Welcome everybody to this new chapter on Introduction to Volumes of Revolution. So this is the second moment of the chapter on applications. We saw last how to find the area between curves. So now we're going to see how we can apply some of the knowledge that we have learned in the previous section into this new section, which is entitled Volumes of Revolution. So we will actually investigate what happens to a region in R2 when it is made to revolve around a straight line. For example, suppose we have a half circle that would be centered at 3, 0 with a radius of 2. Now, what would that look like? Well, if you actually are thinking of something like this. So half a circle in the first quadrant, radius of 2, centered at 3, 0. You are definitely on the right track. So now when this region revolves around the x-axis, we get, what do we get? A sphere in R3 that would actually look like this. So this is a three-dimensional object. So it has depth, it has length, it has width, and it is represented by a sphere. So what else do we have right here? Suppose there's a region bounded by a straight line through the origin. The x-axis is another bound, and the line x is equal to a is yet again another bound. What is it that we have this time around? Well, we have something like this. So basically, some sort of a triangle in the first quadrant with a connecting point at x is equal to a. Now, suppose that this triangular region revolves around the x-axis. What is it that we're going to get? We're going to get, yes, a cone. A cone in, clearly, R3. Well, this is the sort of thing that we are going to investigate in this chapter. Very good, very good. So, now, again, to exemplify, suppose we take a region bounded the parabola y is equal to x squared. We bound this with the y-axis this time, and y is equal to 1. Suppose we actually find the region in the first quadrant. What is it that we actually get when we revolve this around the y-axis? Well, we get some weird thing like this, which looks like a bowl, or if you want, it would be, I don't know, half a boiled egg standing on one of its tip. So I guess a bowl is probably a better image. So obviously, the next thing that we want to know is how do we calculate such volumes? Turns out that calculus is the right tool for the job. To illustrate, let's try to calculate the volume generated when the region bounded by y is equal to r, x is equal to h, x is equal to 0, and y is equal to 0 revolves around the x-axis. What does the region look like? What does the region look like? So y is equal to r, horizontal line, and x is equal to h, vertical line. With my two axes, I definitely get something like that. So good old plain rectangle with a height of r and a width of h. Now let this region spin around the x-axis. If you actually can visualize what this will give us, it'll be indeed a cylinder in R3 with a height of h and a radius of r. Good. So let's see here. What do we have? Let's take some vertical rectangles in this region, just like we did when we're calculating the area of a planar region. When these rectangles taken individually spin around the x-axis, what is it that they actually become? Well, becomes something like this. Something that looks like a flat disk or a loonie, or perhaps if you want a DVD. And clearly, the thinner the rectangle, the flatter the disk will be. Now, if we stack a very large number of these very thin disks inside the cylinder, well, these disks will occupy the entire volume of the cylinder. That is to say, summing up the volumes of all these very thin disks will give us the volume of the cylinder. So let's start by finding the volume of one such disk. Okay, using some sort of basic standard formula that volume is the area of the base times the height, we get that, well, the area of the base, it's clearly a circle, it's pi r squared, times the height of that little disk. And here, the height of the disk corresponds to its thickness. This thickness is the width of the rectangle that revolved around the x-axis. Let's call this thickness delta H. So, here we get the volume of one disk to be, well, volume is equal to the area of the base times the thickness, so pi r squared times delta H. Now, like we did in area, let's take the sum of all the volumes of all the disks, so that the volume of the cylinder is going to be the summation I equals 1 to n of pi r squared delta Hi. Now, again like we did in area, if we take each disk to be infinitely thin, that is, if we take the limit as delta Hi goes to 0 of the volume of the cylinder, we should have the exact volume of this cylinder. Now, this limit, as delta H goes to 0, amounts to the same thing as what other limit? Well, it's the limit as n goes to infinity, where n is the number of disks. So if we take infinitely many disks, we get that the volume of the cylinder is the limit as n goes to infinity, the summation I equals 1 to n of pi r squared delta Hi. But of course you remember, I know you do, that the limit as n goes to infinity of the summation is the good old friend of ours, the integral of pi r squared dh. So if we are to conclude this calculation, let's x is equal to 0 and x is equal to h as the bounds of my integral, so that the volume of the cylinder can now be expressed as this very nice integral from 0 to h of pi r squared dx. What is that integral? Well, pretty easy. You integrate with respect to x, you get pi r squared x between 0 and h. And FTC part 2, bring in the h and bring in the 0, you get pi r squared h, which is the known formula for the volume of a cylinder. Very well. Okay, so now let's take a look at, yet again, another example. This time, when the region bounded by the line y is equal to x, the line x is equal to 1, and the x-axis, this is the region we get. We want to spin this region around the x-axis. So what is the region that we should get here in R2? Well, we've seen that before. It's that triangle that actually is shown here. I've drawn a little rectangle in the region. Now, when this spins around the x-axis, we get that little cone we spoke of before. What I'm showing here is actually 1/4 of the cone with a little quarter of a disc somewhere in its volume. So I'm really showing 1/4 of the entire volume. And the idea now here is going to be to consider the cone as being the superposition of a large number of very thin disks, each one being obtained by rotating a small rectangle in the original planar region. So, for each small disk, the radius r is actually the height of the small rectangle, that is, r is equal to x. As for the thickness, let's call it delta x. Hence, what do we have here? We have that the area of the disk is pi r squared, or in that case, pi x squared, since r is equal to x. And we have that the volume is this quantity multiplied by the thickness, so pi x squared delta x. Taking the sum of all the volumes of all the disks, we actually get, well, the summation of pi x squared delta x. Okay, so take infinitely many of these rectangles, each one, of course, infinitely thin, and we get that the volume of the cone is limit as n goes to infinity, a summation I equals 1 to n of pi x squared delta x. And once again, the limit of the summation is the integral of pi x squared dx. The bounds for that integral were from 0 to 1, if you remember the graph in R2. So that hence the volume of the cone is the integral from 0 to 1 of pi r squared dx. What's that integral? Well, we integrate with respect to x, so the integral of x squared should be x3 over 3 between 0 and 1. Apply FTC part 1, FTC part 2, so the 1 goes in, the 0 goes in. You get pi times 1 cube over 3, or pi over 3 cubic units. Now you may remember that the formula for the volume of a cone, we saw this back in high school, is 1/3 pi r squared h. In this case, what we have is r equals 1 and h equals 1. By replacing these quantities into the formula 1/3 pi r squared h, we get 1/3 pi 1 squared times 1, which is basically pi over 3 cubic units. And this basically concludes the introduction to volumes of revolution. In the next segment, we will look more closely at some applications of the so-called disk method. See you in the second part of this chapter on volumes of revolution.